Sorry about that, just had to click the record button. But yeah, this is a little bit about me, and I will be taking you through the basics of integration today. So for some people, that'll be year 11 content, some it'll be year 12, depending on what maths course you're taking and in what state. But I was from New South Wales, so that is, I'm basing this off what we did. But the rules that I'm going to go through is the basic rule, what integration is, how to do it with a linear function. Then we're going to look at some definitive integrals, which is where you have bounds, it's not infinite, exponentials, fractions, so the 3 different ways that a fraction can be integrated, and the area under the curve for a fraction. Or not for a fraction, sorry, just the area under a curve. So I think that because what's the time? It's 1:03. Let's just get into it. We have a lot to get through and not a lot of time. So the basic rule, it's the exact reverse of differentiation. So when we differentiate something, we bring the power down and we subtract 1 from the power. So we're doing the opposite of that here. So we're going to be adding 1 to the power and then dividing by our new power. It's important that you remember that that is your new power and not your old one. And the other thing to remember is your plus C. They will mark you down if you do not include your plus C. So please make sure that you do. But that shouldn't be too new to any of you. So I'm going to move on to our next rule before we start an example. So linear functions, it's the exact same rule as you can see. The only difference is that we have more than just x inside of our brackets. We have an ax plus b. There doesn't need to be a b, it could just be an a. If it was, that would kind of be redundant though. They could have just put the power to the a and it would work separately. So most of the time, this is the form you're going to get it in. And the only extra step that you need to remember is that this a is going to be divided by there as well. Now, the reason why that is if we took an example of a function, let's say 3x plus 4 to the power of 5, if we were to differentiate that, we're going to be using the chain rule. So the chain rule, most of you should be familiar with, we're going to be taking the 5 down, leaving the 3x plus 4, subtracting 1 from the power, and then multiplying by our f dash of x. Now, when something is linear, the f dash of x is just going to be that coefficient. So see how we're multiplying by the coefficient of x there in our chain rule. That's why we also have to divide by it when we're integrating, remembering that integration is just the exact opposite of what you were doing in differentiation. So this was an example of differentiation, but obviously you could work it backwards. So that's why I didn't have a plus C there or anything. Okay, let's get into our first example question. So this is going to use those rules that we just did plus an extra one, which is our definitive integral. So with our definitive integral, we have bounds. And so what that means is we're looking from one section of the function to the next. And so we're going to be we're going to integrate first. That's what these big square brackets mean. So going from the lowercase f to the capital F of x. And then we are going to sub in b and we're going to sub in a, remembering that we're subtracting. So the order is important there. So I'm just going to write a note on the side. Order is important. Okay, I'm going to start on this example. If you can do it faster than me, great. Try and keep up and do it with me, and drop any questions in the chat the Q&A, if you have any. Okay, so if we want to integrate this, the first step that we're going to have to do is we're going to have to put our big square brackets here. We're going to add 1 to the power, which is going to give us 4. And then we're going to divide by the 4, but also don't forget that you have to multiply that by your coefficient. So times by 2 there, and then we're going to have 3 and 1. So now what we've got to do is we've got to sub in our 3 and our 1. So we're going to have 2 times 3, which is 6, plus 4 is 10. So we're going to have 10 to the power of 4 divided by 8. And then we're going to subtract, remembering that that's important to go down to our a. 2 times 1 is just 2, plus 4 is 6 to the power of 4 on 8. And then I'm going to put that in my calculator. 10 to the power of 4 minus 6 to the power of 4 is, on 8, sorry, is going to give me 1,088. Now, a common question that I don't think is really explained in the classroom is, well, where did the C go? Because I was just saying it's super important that you don't forget it here. You're going to get marked down if you don't have it. Where has it gone? The reason we don't have to include this is just imagine that we did. Let's say we had a plus c in there just for argument's sake. Here we would have a plus c like this. Here we would have a plus c like that. What you can see is that if we expand these brackets, this c gets canceled out by this negative c. And so it becomes c minus c, which is 0. And so we don't need to include the c just for definitive integrals. Otherwise, it's important to include it because that's how your constant, it doesn't appear in your derivative. And so what we're doing is we're taking the derivative and going back to the original function. So you need to say, well, there could have been literally any constant here. So definitive integral don't need plus c. Okay, I'm not seeing any questions in the chat, which is a good thing, I'm hoping. So I am going to move on to our next rule. This is called Speedy Seminars for a reason. We go through things quite fast. So I wanted to deal with exponentials next. And if you were in the differentiation workshop, we talked about the ln(a) or the base a when we do this. And so I thought it was important to show you that again here. So with our e to the power of bx, we can't use this for just any f of x. If we had a nonlinear power, this wouldn't work. We'd have to use a different rule, which is only covered in the very high levels of maths. But if we have something like this, don't know why that has suddenly changed to an a there. Just imagine that this is a b. What we're going to be doing is we are just going to be dividing by our coefficient of x there, because remembering your derivative of e to the ax, you're gonna bring your power, the coefficient of your power down. So if we're multiplying when we're doing differentiation, we're dividing when we are doing integration. So that's the basic rule here. Now, if we don't have a base e, we need to do a little bit extra, and I think this often gets forgotten at schools. So the reason we have to then add this divided by ln(a) is because we're actually doing that here as well. We just don't need to write it, because if you put ln(e) into your calculator, if you don't know what it is already, it just gives you 1. So multiplying anything by 1 is kind of pointless, right? So they don't teach you that when you're using your natural log, and that's why e is such a special number, because it can simplify really easily for us, and on the graphs it's really nice. It has good intercepts, all of that sort of thing. But we need to not forget it here. So if we go back to when we're differentiating, if I was differentiating a to the bx, when I differentiate it, I have to multiply by ln(a), multiply by b, and I get a to the bx. So if I'm multiplying here, again, the same thing goes, and I have to divide. So it's important that you remember this rule. It comes up at the end of exams as like something that's difficult and students often forget, which is really annoying because you know the rules and you just don't know that extra little application. What I mean by a is a constant, so literally anything besides for me like 3, 4, 5, not something like x. Okay. Did I have an example for this one? I did not have an example. Let's just go through one quickly on the bottom of the slide. So if we did the integral of 4 to the power of 5x dx, I'll give you a second to get a head start on me so that you can see if you know what you're doing here. Hopefully that's long enough for you to start thinking about what you would have written. So what I would do here is I do 1 divided by ln. My a is going to be the 4 because it's the base there. Then I'm going to do times by 1 over 5 because that's the coefficient of my power there. And then I'm going to multiply it by my original situation that I had going on. And I'm not going to forget to plus c at the end. If you wanted to simplify it, you could say 1 on 5 ln 4 times 4 to the 5x plus c. And that would be your final answer there. So hopefully that makes sense and it's fairly straightforward. I think that it's an important thing to get your head around, but once you understand it, it's just applying that rule over and over again. Okay, now fractions. This one I think is a little bit more complicated, which is why I wanted to go through it and spend quite a large portion of our time today on it. So a lot of the time teachers will focus on this, and that will be the only rule that they teach. And so it would make sense if I'm going, okay, I'm doing exponentials now, I'll do logs. But what I found is that they didn't tell you that there's also these. So a lot of the time you see a fraction and the first thing that your mind does is go, it's going to be a log. And then you don't have the right amount of x's in the right places. And you're like, oh my God, I can't do this question. But what I'm showing you here is that there are actually 3 different ways you can do it. And the other 2 are kind of like common sense that they think you would just know and they don't have to teach you. So we'll go through the log rule first with an example. And then once we've done that, I'll be like, okay, if it doesn't meet these conditions, this is how you can tackle that question. So if my example was the integral of x over x squared plus 4 dx. Now, for me to be able to turn it into a log, I need to have my f dash x over my f of x. Now, the important thing to remember here is you can't magic up an x. That's what I'm going to call it. You can't magic up an x, but you can do whatever you want with coefficients, pretty much. You can multiply and divide, and they cancel each other out, right? Like if you multiply something by 2 and then you divide it by 2, that is going to make it just 1, and it hasn't changed the value. So you can do what you want with coefficients as long as it doesn't change the value. That was a longer piece of writing than I thought it was going to be. Okay, but let's use this example. So if your f of x, the first place you have to start is you have to look at your denominator and you say, okay, so my f of x is going to be x squared plus 4. Do some simple differentiation here, and we're going to get that our derivative is 2x. Now, do I have 2x? No. But do I have the right power of x? So I don't have an x squared, I have an x, we want an x. So I have the right power of x, which means that this thing about not being able to magic up an x isn't going to be an issue. I can deal with that. But I need to get this 2 in there somehow. So what I'm going to do is I'm going to multiply it by 2. I'm just going to do that in a different color so that, that's not what I wanted to do. Okay, apparently I can't do a different color for some reason, so we're just gonna have to stay in red. Hopefully you can follow along. But I'm gonna multiply it by 2. Now, if I'm multiplying by 2, how do I undo that? I divide by 2, so I'm gonna chuck a half out the front because that's just like dividing by 2. And so now this is the same value as that original question that I had there, but I've got my f dash x over my f of x. So once you've done that, you can be like, great, all the conditions in my rule are satisfied. I can just plug it into this. Don't forget that if you've put that coefficient out the front, you're going to still have a coefficient here. So we're going to have that half, then we're going to have ln. Absolute value is important. In this question, you're never going to have a negative value of your f dash of x. Why? Because you've got an x squared and you've got a plus, but some ones you can. So just make sure you do the absolute value, and then don't forget your plus c. So that is how you end up with a log. Now, here I was hammering on about base A. When we're integrating, because we don't actually start with that log, we create the ln, so we're never going to have a situation where we've got not base E because we create the log. So don't worry about that here. Any questions about how to do this integration? I found that in the past, some students will know that they need to get it in this form, but they'll forget what to do after that. So it's using your denominator. You always want to interrogate your denominator. One way to look at questions and recognize very quickly whether you're going to be able to use this rule or not is if you have your x in your denominator needs to be 1 power higher than your x in your numerator. So if I had x cubed in x, I know that's not going to work. If I had x and x to the 4 on the top, I know that's not going to work, because thinking about differentiation logically, you know that you're subtracting 1 from the power. So that's how you end up with this on top. Now, these examples that I've written over here, you can see that that's not the case. You don't have 1 less in your, you don't have 1 less up there. So I'm going to try and get the eraser to work. but it doesn't seem to want to. Okay, so I'm just gonna have to write on this black slide. So the example here is x to the power of 5 minus 2x squared, x to the power of 5 minus 2x squared, all over x to the 4. Now, the reason I've called this 7 fractions is because if you can see here, we can actually just simplify it. We don't need to use any fancy rules. So the simplification of this, we're going to split it up, x to the 5 on x to the 4, minus 2x squared on x to the 4, which is going to give us just, oh, sorry. Dun, 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 dun. Well, let me go back to it. No, it's erased. Okay, I'm going to have to try and do this again quickly. X to the 5 minus 2x to the 4 on x. Oh, that was squared, I think. Okay, so that's going to leave us with x minus 2 on x squared, right? Because I'm just splitting it and then doing that. And then from here, integrating this is a lot easier than integrating this one here, because you would try and use your log rule and you can't do it there. Okay, integrating this just for completeness sake, let's actually do the integration. So we're going to have x to the power of 1. We're going to add 1 to that power, so it's going to become x squared, and we're going to divide by our new power, which gives us a half. Now we're going to do the second one. This is actually what I've said my third way of doing fractions is, because see, there's no x on the top. So when there is no x up here, and this power is not 1, what we can do is we can treat it as a negative indice. So this expression here, the 2 over x squared, is actually 2 times x to the negative 2. So the important thing there is if we're adding 1 to negative 2, we're going to end up with negative 1. So we're going to keep our negative 2 as our constant out there. Then we're going to have to multiply by our new power, which is negative 1, and have it like that. Don't forget to add c. But then if we just simplify this, the negative times the negative is going to give us a positive. We're also just going to get rid of that 1 because it's not helping us in any way. And we're going to be left with an expression that looks like that. So always make sure to check for what conditions you have. This, we had no x in the numerator. So that's how we were able to use the negative indice rule, is what I'm going to call it. Here we had x's, but we could simplify. And so always check to simplify first. And then the only time you're going to be using that log rule is, if I can go back to my slides, if we have the f dash x on the f of x, but we can change our constants. So really the important thing that you need to remember to look for is if you have x is 1 higher power in the denominator than the x that you have in the numerator. If you don't have that condition, this rule isn't going to work. Okay, I'm going to take a bit of a breath for like 2 seconds just to see if anyone has any questions which they want to type into the chat. As you can see, we're on slide 9 of 10. The last slide that we have is going to be on area under a curve. I've given myself more writing space on this one, which is good. So it's going to be a little bit longer of a question because there are a few steps to it. Okay, no questions are popping up. Hopefully that means that we're all on board. So let's go through area under a curve. Okay, so what I've put in my little notes here is that our first step is to see where the graph is above or below the axis. So when we're integrating normally, what we're doing is, if I drew just like a regular sort of parabola here, when we're dealing with this, if I was to integrate from here to there, this section that I've just scribbled in there, that is going to be a positive number. And then if I scribble in a second little section here, because it's under the axis is going to be a negative value. And so when we integrate, when it's not asking us for the area and we just integrate, the calculation does that for us. But what it ends up doing is it goes this bit minus that bit. And so when we actually want to find the area, we don't want to subtract that bit, right? We want to have that as a positive number because area is about the size that's there, not whether it's located above or below the axis. So when I'm talking about area under the curve, what I'm talking about is trying to neutralize the effects of the x-axis and to actually find what the physical area is between the curve and the axis. So how we do that is if I label these points, if I label it, I don't know why I did C and D, it probably should have been A, B, and then B, C. So if this is A, B, and C here, the A to B area is positive, so we can just deal with that, that's fine. And then what we want to do is we want to subtract this, because if you subtract a negative, it becomes a positive. If that's confusing for you, another way that it can be thought about is you still want to add it, but you want to add the absolute value of it. It's probably a little bit more correct. So that's how you're going to get the entire area. Now, this is kind of the questions that we could get, and so I wanted to go through an example as it is a little bit more of a tricky concept. So x squared minus x minus 12, hopefully you can look at that, look at the leading term and recognize it's going to be a parabola. What we then need to do is we need to graph it, because you need to, that's what I'm saying by first step. First step, see where it's above and below the axis. You're not going to know unless you have, unless you have graphed it. So we're going to need to start, that's our first step. Now the first step, we can see that this parabola is going to be concave up because it has a positive leading term. So we just need to find what our x-intercepts are to work out whereabouts it's going to change from being positive to negative. So if we factorize this, what multiplies to give negative 12 and adds to give negative 1, I would say is x minus 4 times x plus 3. Does that work? Yes, that works. Okay, that's great. So that's going to be our f of x. Now, if we drew this little postage stamp, our x-intercepts are going to be negative 3 and 4. So we got negative 3, and then we've got positive 4 out there. This is not to scale. It doesn't need to be to scale in your exam either. It's just for you to literally be able to see what you're doing. So we're going to have a graph that looks something like that. Now we're going to have 2 here. This is 4. And then we're going to have 7 out there somewhere. So what we can see is, just like in my little diagram up here, we have a negative area and we have a positive area. The reason why I chose this side of the graph when I was writing this question is because I wanted to show you that the negative could be the first bit, so don't follow this too strictly. That's just an illustrative rule. So the first one that we're going to have to do is put absolute values around the 2 to 4 integral. So absolute value of the integral from 2 to 4 of x squared minus x minus 12 dx, absolute value plus, and then the 4 to 7 is very straightforward. It's just a normal integration there. Okay, so that is the way you would set up this equation. Now let's solve it. So again, using our basic integration rules, make sure you keep that absolute value. The reason why I prefer to use the negative sign is because I always forget to draw my absolute values. But we're going to have a third x cubed minus a half x squared minus 12x. 4 and 2, using that definitive integral rules that we were talking about earlier. Then we're going to add the exact same thing because it's the same function. Then we're going to do this, and then our bounds are going to be 7 and 4. So what we have to do next is then plug in 4 and 2, and then plug in 7 and 4. So I'm not going to write that out for the entire thing because I'm pretty sure most of you would know how to plug in numbers into your calculator. But if I put it into mine really quickly, so we're going to have a third, half, and 12. Okay, so if I plug in 4, I get negative 104 on 3, and then I'm going to have to subtract whatever I get for 2, which gives me negative 70 on 3. So don't forget that there's a double negative there. The other thing that I like to check at this stage is, did that actually give me a negative number that I'm going to need to absolute value? Because if it didn't, then the way you drew your graph was wrong. So yeah, that gives me negative 34 on 3. So we're left with a negative number inside here, and we have the absolute value, so it'll give us positive 34 on 3. I'm just going to write that over here. Then the next step that we have, we're going to put in 7. So that gives us negative 34 on 3 minus what we got for 4, which is the same as before, negative 104 on 3. So we have 34 on 3 minus 34 on 3 plus 104 on 3. So our answer is going to be 104 on 3, like that. Okay, well, it is 1:28. I was worried we weren't going to get through all of that in only half an hour, but we got through heaps today. So hopefully that was helpful. I'll stick around for the next minute or two, just if any questions pop up in the Q&A. But otherwise, thank you for coming today, and hopefully I'll see you next time. Okay, it looks like and no one has any questions, so I'm going to end the meeting here. But again, thank you all so much for coming.